Recording in progress.
Hi students, in this lecture I am going to discuss problems based on collisions 1D. Let us see first one. See the question carefully. A body of mass m makes a head-on elastic collision with a stationary body of mass M, and condition is M is very small. Find their velocities after the collision. So condition is here. Lighter body is colliding with a heavier body which is stationary. Head-on elastic collision, right? And second case is heavier body is making collision with a stationary lighter body. Okay, let us see the first one. First one is lighter body making collision with heavier body which is at rest. Let us see. So first one, lighter body making collision with a heavier body. Lighter body with a stationary heavier body. You can say U1 is equal to U2 equal to 0. This is a capital M. Condition is M, very small compared to capital M, right? Head-on elastic collision, so E value is 1. So first we have to write momentum conservation. So writing here LCM, M into U should be equal to, after collision, take velocity V1, which we have to calculate, plus capital into V2. See number of unknowns, V1, V2, two unknowns, right? So we require one more equation, that is coefficient of restitution, that is E value V2n minus V1n upon U1n minus U2n. See how much we get? V2n, that is V2, minus V1, okay, V1n. Because in one-dimensional collision, U1 is nothing but U1n, U2 is nothing but U2n, okay. This is equal to U1n, that is U1, right? Let us now simplify these two equations. So here I can write in the place of V1, see what we can write. In first equation, mu equal to m into, in the place of V1, V2 minus U1. U1 is nothing but U, right? Plus MV2. Remain just a calculation part. Mu, 2mu. That is equal to M plus M into V2. Okay. That means V2 value 2mu by M plus M. Okay. And condition is M is very small compared to capital M. So this will be approximately equal to capital M. So this is approximately equal to 2mu by capital M. Now small m by capital M is almost 0, right? So approximately how much? It is approximately 0. That means heavier body almost at rest. Getting the point. When lighter body makes head-on elastic collision, heavier body almost at rest, it won't move. Let us see what about V1. V1. Focus second equation. V2 value almost 0 means V1 equal to minus U1 approximately, okay? Approximately equal to minus U1. See meaning of minus. Before collision, first body was moving right side. After collision, it moves back. Getting the point. This is almost at rest. This is now reversing. Almost the same speed, it moves back. So like this, we can solve directly by using momentum conservation and coefficient of restitution. Okay. See now next case. Next case is heavier body is moving, lighter body is at rest. Right now case is reversed. See carefully. Lighter body at rest, heavier body is moving. Heavier body having velocity u. This is a Kaplan. Taking u1 equal to u. Lighter body, small m, is at rest. So u2 value 0. Again, head-on elastic collision. So write again equations. According to LCM, m into u should be equal to m into v1 plus m into v2. So when we are not knowing directions of v1, v2, we assume they are post. Okay. Next coefficient of restitution, that is v2n minus v1n upon u1n minus u2n. This is equal to 1, right? In the place of v2n, it is v2 only. v1n, that is v1. u1n, that is u1 minus u2. u1 means it is u, right? u1 means it is u. Okay. It is u. And this is 0. So from this, see what we get. V2 minus V1 is equal to u. That is now second one. Now see, substitute this result in equation 1. From equation 1, mu is equal to, in the place of V1, see what I can write in the place of V1. It is V2 minus u, right? Plus mv2. So just matter of writing LCM and coefficient of restitution. Then see what we get. 2 capital U is equal to capital M plus small m into V2. Okay. So V2 means velocity of the lighter body. So V2 equal to, see here what I can write, 2mu by m plus small m. Capital M is very large compared to small m. So this is approximately capital M, right? Approximately capital M. So 2 capital M u by capital M. Capital M gets cancelled. This is approximately equal to approximately 2u. Its meaning is lighter body moves with double the velocity of the heavier body. Getting it? Its meaning is lighter body is moving with double the velocity of the heavier body. Let us now focus what is V1. V1 equal to, see how much? In the place of V1, V2 minus u. V2 value approximately 2u, right? 2u minus u, approximately u. That means heavier body continues in the same direction almost with the same velocity, right? That is a conclusion of these two. Students, if you are taking equal masses, see what happens if you take equal masses. I will write here. If you take equal masses means equation 1 becomes mass gets cancelled, right? Mass gets cancelled. Or let us take like this. Velocity u1 bar. Second one, velocity u2 bar. When you are taking equal masses, m into u1 bar plus u2 bar. This is momentum before collision. That is equal to m into momentum after collision. v1 bar plus v2 bar. Momentum after collision. Mass gets cancelled. So u1 bar plus u2 bar equal to v1 bar plus v2 bar. Okay. Equation 1 LCM. Next, focus coefficient of restitution. Focus now coefficient of restitution. Since E value is 1, I can take directly here V2 bar minus V1 bar is equal to here U1 bar minus U1 bar minus U2 bar. Okay. So we got now conditions like V1 bar from LCM V1 bar plus V2 bar equal to U1 bar plus U2 bar. Now solve this two, then see what we get. See what is our final result. If I'm taking sum of these two gets cancelled. 2 U1 bar equal to 2 U1 bar equal to, you can see here, minus V1 bar plus V1 bar. Take sum of those two. Sum of those two gives V1 bar cancel, U2 bar cancel. So 2 U1 bar equal to 2 U1 bar is equal to 2 V2 bar. 2 gets cancelled. U1 bar equal to V2 bar. That means velocity of the second body is equal to velocity of the first body before collision. Okay. Now substitute this in this equation, in the above equation, then see what we get. V1 bar equal to, it is U2 bar. Check once. I have taken U1 bar equal to means in the place of V2 bar. In the place of V2 bar, okay. We can write U1 bar. If you take U1 bar here, U1 bar cancel. V1 bar equal to U2 bar. That means if you take a head-on elastic collision and masses are equal, then they exchange their velocities. Okay. So keep these points in mind because we use frequently these results. Let us see next one. Right, see the question carefully. A body X with a momentum P collides with another identical stationary body Y one-dimensionally. During the collision, Y gives an impulse J to the body X. Then the coefficient of restitution is, okay, let us write down the given conditions. X has momentum P and Y initially at rest. Y gives impulse J to the body X. Now first write down the given data. X. It has a momentum P. Y stationary. After collision, what happened? This Y gives impulse J to body X. And we have learned that net impulse equal to change in momentum. So in this case, during collision time, force by Y on X or by X on Y is very large. It is impulsive force. So because of impulsive force, impulse equal to change in momentum because we neglect remaining all forces. So that impulsive force becomes net force. And impulse of net force is change in momentum. That means this becomes now P minus J, its momentum will be J. And if you take sum, total equal to P. Okay, right. Now let us take coefficient of restitution V2n minus V1n upon U1n minus U2n. It is one dimensional collision, that's fine. That V2 itself is V2n, V1 itself is V1n, U1 itself is U1n, in the same way U2n. Okay, so V2, I am taking this as a first body and this is second body. Therefore, for second body velocity, I can write J by M because J is momentum. Momentum by mass gives velocity minus V1 momentum P minus J upon M, that is velocity, by U1N, U1 is now P minus J. Wait, it is U1, right? Not V1. U1, U1 is, it is P by M, right? Initial velocity. M gets cancelled. J minus P minus of minus plus J. It is 2J minus P by P, or it is equal to 2J by P minus 1. It is just taking that momentum conservation, then coefficient of restitution, right? See next one. See the question carefully. A particle of mass 100 gram moving at an initial speed u collides with another particle of same mass kept initially at rest. If the total kinetic energy becomes zero point 0.2 joule after the collision, what could be the minimum and maximum value of U? Okay, so this question is taken from H.C. Verma. Let us see mass 100 gram given identical particle. Total kinetic energy becomes zero point 0.2. Finding minimum and maximum value of U. Right, see carefully. So first write down the given data. Identical masses. Mass is given 100 gram. Identical. This also M only. This has velocity U. After collision, for the system kinetic energy for system after collision, okay, after collision becomes 0.2, right? So if you take energy conservation, we can write kinetic energy before collision half mu square, that is equal to kinetic energy after collision 0.2 plus loss in kinetic energy. Okay, this is present final value plus loss totally equal to initial value, right? Now focus what is loss. What is loss? Students, if you remember, mass m1, velocity u1, second one mass m2, velocity u2. If collision is elastic, collision is inelastic, means taking E value, we can find initially kinetic energy, means before collision, of m1 u1 square plus half m2 u2 square. That is the kinetic energy for system before collision. Coming to after collision for system, half m1 v1 square plus half m2 v2 square. Now, if you subtract final kinetic energy from initial one, then we get loss in kinetic energy. And that comes out to be, after making calculation, half mu v relative square into 1 minus c square. Here mu means reduced mass, which is equal to m1 m2 by m1 plus m2. Okay, right. Now coming to here, in our problem, given identical masses. Okay, then see delta k how much? Delta k equal to half m into m by m plus m. M into m by m plus m. It becomes m by 2 into v relative square. Okay, v relative square that we cannot change. V relative square into 1 minus e square. So in this case, what happens is v relative is equal to u. How much? V relative, because 1 is at rest, u minus 0, that is equal to u. Okay. Now see carefully. If delta k is maximum, then total value is maximum. That means u value maximum, right? That means if loss in kinetic energy maximum, u value maximum. If delta k is 0, then u value will be minimum. So delta k 0 means kinetic energy before collision and after collision same. It is elastic collision. Okay. See, come here. If E value 1, delta k becomes 0. So elastic collision, no loss of kinetic energy. But if E value 0, then loss will be maximum. And that loss equal to, you can see here, half into half mu square. It is a half of the kinetic energy, right? It is half of the kinetic energy. That means when one body is at rest, other body is moving, both have identical masses, then maximum loss in kinetic energy is half of the kinetic energy. So here what I can do is, to find u maximum, I am taking here 0.2 plus half of the kinetic energy. This is maximum loss, right? So u is now maximum, right? 1 by 4, 1 by 2. 1 by 2 minus 1 by 4. It is 1 by 4. 1 by 4. M value 100 gram means 10 power minus 1. U square is equal to 0.2. That implies U maximum is equal to 0.8. This is now 1 by 10 becomes 8. It is now 2 root 2. That is maximum speed. If delta k is 0, then speed is minimum. Then see how much we get? Half mass 10 power minus 1 u square equal to 0.2. Then u minimum, how much? 2 into 0.2, 0.4. 1 by 10 means it is a 4. So u minimum, that is equal to 2 meter per second. So you can keep this result in mind. Loss in kinetic energy in inelastic collision, head-on inelastic collision, half mu v relative square into 1 minus e square. This is expression for loss in kinetic energy in a head-on inelastic collision. Head-on inelastic collision. In this E value 0, there is no loss, elastic collision. E value, E value is 1. E value is 1, head-on elastic collision, E value 1, no loss in kinetic energy. If E value is 0, loss is maximum. Means if you are fixing mu value, V relative. So for these values, when E value becomes 0, loss is maximum. Okay. So we use this result frequently. That is about the question.